Don't drink and drive. Okay, so let's go through this a little bit. Let's do a lighter note. Multiple degree of freedom systems.
Do like a quick review.
I'll do a quick review, sure. Because you weren't here.
Yeah.
Neither was Cash.
James is live for you.
Yep.
It's worth it. I always do it. I really did it anyway. So you set it up, right? You set it up, and it's linked together, right? It's always worth doing this anyway, just revisit. So what's happening at mass 1 is going to be affected by what's happening at mass 2 because they're connected to K2 by K2. So if mass 2 is moving, it's going to be affecting what's happening to mass 1. I'm reviewing for you, Cash. Are you paying attention?
I studied over the weekend.
Oh, you did.
I actually gave out a password, so
I
You gave out a
know.
password
I'm not
to
supposed to
Repost
listen to it.
Yeah, I did it. Well, let me know when you're ready.
I'm ready.
Okay.
I just got done making up my notes.
You got your Minnesota shirt you just got, brand new.
It's brand new.
Brand new,
3 days old, actually.
And so it's equivalent to this system over here. This guy is right here. We talked about, you draw a free body diagram of it, and you can assemble what this is. You end up with a system of differential equations that look like this, where what's happening at U2 is affected by what's happening at U1 and vice versa, because you can see right here, U2 shows up in the U1 differential equation, and then U1 shows up in the U2 differential equation. So how you solve that system of differential equations is very difficult, right? There are methods out there for doing it, right? They're similar to like substitution and stuff that you do, like if you have a regular system of equations instead of a system of differential equations. But they're very difficult. They're very few actual solutions that you can, methods that you can actually, or equations you can actually solve it for. So that you could do numerical solutions is one way to do it, or you could do modal analysis, which we are going to do. We're going to do modal analysis, right? You can write this thing in matrix notation. We talked about matrix notation. We talked about assembling the matrix in a controversial way, right, Jacques? The master slave, which Jacques took issue with the terminology, which I think, yes, you're right. We should call it something else, but that is a class where you move one mass and you look to see what it does to the other things, where you hold everything steady. So you have you move one and you look to see what it does to mass 2, and then you see what that same thing does to mass 1 and what it does to mass 3, and then you assemble this stiffness matrix. We're not going to have to do this very often, right? I think this is by hand when we do our calculations. This is the most complicated one that we do. Other types of systems out there that have multiple degree of freedom systems are, right, this thing we could define as being U1 and U2, and that would define the motion of this thing, because you can imagine this thing kind of flopping around. There's that, there's this is what VA does, right? It has multiple degrees of freedom per node, right? Rotations at each one, and in fact, if you have a 3D model, it has 3 rotations and 3 displacements per node, so you have 6 degrees of freedom per node, and really it's handling all of those things. It's assembling a big stiffness matrix, a big mass matrix associated with that, and whatnot. This is another one where you have displacement. You can define the displacement. This is a plan view of a model, and you imagine looking down on this. You could have a displacement, and a rotation would define everything. And then this one was kind of neat. Depending on how you formulate this, you can have it either coupled, right? These off-diagonal terms are where you get the coupling. You can have it coupled through the stiffness matrix, like this one is here, if we set it up like that, or it can be coupled through the mass matrix, and you have an uncoupled stiffness matrix and coupled mass matrix. So you can formulate it 2 different ways. Modal analysis works for both of these. It works for coupled mass matrices and coupled stiffness matrices. But we're going to be sticking to this type of system, right? We're going to be talking about this type of system. But everything we do, all the methods that we use apply to all these systems, right? And like VA will do exactly what we're doing for a system like this, right? It just gets too complicated. You can't do it by hand. So we just stick to the very simple shear frames, basically. Okay. This is where we left off, right? Free vibration. I'm going to be telling that story for years. We're just at the end of single degree freedom system, and the guy goes, I won't use your name. I might. I mean, nobody will know, like, in the future. They would, like, next time I teach this 2 years from now, hopefully none of you are in it, right? So, some of you may, but if you, nobody will be in it, and then we'll say, like, Ethan, they'll be like, who's Ethan? And then...
It's an inspiring story. Like, I went from there to, doing okay on the exam.
Yeah, you did. Yeah, you did. You did. You did. Somehow. Somehow. You were just missing that one piece of
That's all I
information,
needed.
and then once you got that, you soared. All right, so free vibration. So this is a multiple degree of freedom system. We're going to pull it back and we're going to let go of it. This is exactly how we started single degree of freedom systems, and that's how we started here, right? And we actually follow the same process, right? So this is writing it in matrix notation. This is the same free vibration. All of it's equal to 0. Now, though, our 0 isn't just a number; it actually is a vector. This, and you can't. Right, I can't solve, this is that differential equation. I can't solve this by itself because what's happening is affected by U2 because of this negative K2. We do matrix math that gets multiplied, so it's K2 times U2, so I can't solve this thing in its current form. Right? Anyways, come back to this. What we did for single degree of freedom system, let's just look back what we did. What we did for SDOF, our single degree of freedom system, there, right? It was the same deal. MU double dot plus KU was equal to 0, right? And what we did is we said, yep, let's make an assumed form of the solution. Say U is equal to C times E to the I omega T. We assumed that form. Taking the derivative of that, the second derivative of it, the acceleration, that just becomes negative omega squared C e to the I omega t. And so you assume that form of that solution, you take the second derivative of it, there's that omega squared comes out. You then plug that stuff back into the original equation. And what you get is negative m omega squared times c e to the I omega t plus k times c e to the I omega t. That's what we did before. This is just a kind of review. Right. And then that's all equal to 0. You can kind of divide by the EI to the omega t, right? So that goes away, that goes away. And what you get is negative m omega squared plus k is equal to 0, which then led us to omega squared was equal to k over m. Right, that's where that came from. In order to solve this differential equation, what popped out of it was omega squared had to be equal to k over m, or omega was equal to square root of k over m. If that doesn't happen, you can't solve this thing, right? And then there's a whole bunch of other stuff we did after that. But the reason I'm laying it out here is because we're going to do the same thing for multiple degree of freedom systems here, right? We're going to kind of assume a form of the solution, and we're going to work our way through, and then something has to be true in order for it to work. Okay. So that's what we do. We come in and say, all right, so for this multiple degree, so that was what SDOF, and what we do here is we come in and say, yep, displacement U1 and U2, right? Displacement of floor 1 and floor 2. We're going to assume the solution looks like this, right? It's got this phi factor out front, or phi vector out front, and then we're going to assume that it's equal to that phi, that shape function, times e I to omega t. So this is the assumed form. Right? What does that look like? Well, that phi is just a vector, right? And then we'll explain why there's two things here, but one's floor 1, one's floor 2, and then the other number is associated with which is eigenvector we're talking about. There's multiple eigenvectors, which we'll get to that in a second, but that's why there's two numbers there. But it's a vector out front multiplied by ei to the omega t, okay? Then if I take the derivative of this, right, same deal, I get this omega squared, just like we did up above, right? That omega squared comes out from this omega right here. When you take the derivative of ei to the omega t, those omega comes out, and you do it twice, so then we end up with negative omega squared, that phi vector multiplied by omega ei to the omega t. Okay, we then take that, this new stuff, and we substitute it in. So then this goes, this right here goes, nope, what am I, good enough, oop, not there, it goes here. Close enough. That guy goes there, and then this guy goes here. Right? You just take that assumed form, plug them in there. That's what we get. And so when you do that, this is what we get right here. Okay. Then we could pull the phi. They're both multiplied by phi ei to the omega t, so that can come out of it. So we pull that out of it, and it looks like this. M, the mass matrix, times negative omega squared, which is just a vector, or which is a scalar, plus k is equal to this right here. Just like that. And then really, this thing could go to 0. Right, you just divide both sides by that. Divide both sides by that, so that goes away. So what you're left with is this. What you're left with is that. Right? And then you can kind of rearrange this by, I mean, you can't divide by the mass. Right? Like here, right, if it's an algebraic equation, I can divide both sides by the mass, but you can't divide matrices. You can't divide by the mass in this case, but you can multiply by the inverse. So just kind of rearranging this, so I pre-multiply by the inverse. And so m to the negative 1 times m gives me the identity matrix, which just kind of gives it, it's like it equal to 1 basically. And so that's negative omega squared, and so then I got the m to the negative 1 times k. So that's all we've done there, just kind of moved that mass matrix, right? And so what this is right here is a classic eigenvalue problem. All right, we'll talk about that here. Value. Classic. They're so fun. I find, I guess eigenvector is one word. I personally love eigenvalues and eigenvectors. They're really neat. Right? I'm also not in the real world. You guys don't be whipping out eigenvalues and eigenvectors at work. Okay? You're pissing people off if you do that. Okay? Don't do that. But that's a classic eigenvalue eigenvector problem. It's kind of in a weird form. Right? I could rearrange it. You don't have this. You don't have this one. Right? I understand that. Right? But I just rearranged this equation. It is down here. No, it's down on one of the lower ones. I've just rearranged it to look like this one, right? And this is. So you see what I did? I just moved one thing to the other side of the equation. Okay? I moved that negative omega squared over to the right hand side, right? So this right here is more noticeable. What the classic eigenvalue problem is right there, and what it is, a classic eigenvalue problem is a matrix. Right? A is a matrix. Matrix times a vector is equal to a scalar times a vector. Right? The same vector, I should say. That's the important thing to note. This is where they're matrix times a vector is equal to a scalar times that same vector. That's a classic one, right? Where I first learned about them was trying to make something more numerically, or less numerically intensive, right? So I could either carry, they get used in summations and stuff. You use eigenvalues and eigenvectors, because if you think about this, if I'm taking a matrix and then multiply it by a vector, I have to do matrix multiplication, right? I gotta go boop, 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 right? And I gotta go boop, add them up, boop, add them up, boop, add them up, boop, add them up, boop, add them up. Hey, you know what I'm talking about? No. You do too. Just matrix math, right? You gotta go your vector, multiply it by your matrix, add them up as you go across, and that gives you that one. Then you gotta go to the next one, add them up, gives the next one, gives the next one, right? I could do that, or If I knew what this special scalar was, I just do scalar multiplication, right? And so instead of doing that, which is very numerically intensive doing this part of it, if I knew what that scalar is, then I just have to do the scalar times that vector. And so it's way less number of calculations, right? And so these eigenvalues and eigenvectors get used in that sense. Like if you're doing like a summation or something like that, and you're adding them up, and you want to speed things up, you use eigenvalues and eigenvectors because it's way less numerically intensive. In this case, it's not how we're using them, but that's what's special about it. So x and lambda, you know, if it's the same x, those are actually properties of that matrix, right? Of matrix A, right?
So could every vector be an eigenvector?
Could a vector no, I think that's going backwards with it. Maybe, there might be a matrix out there somewhere that matches with the vector that you have, but that's good. Don't do it that way.
Well, isn't like,
Don't think of it that way.
we're saying that for every for a vector multiplied by a matrix, there's like a scalar that can replace that matrix and
Yes.
do the same thing.
Right, and I see what you're saying. So then if I have a vector, could I find a matrix and a scalar that went with that?
Mm-hmm.
That's going backwards. There probably is a way of doing it, but that's backwards. I want to think of it more of, I have a matrix and I want to find a scalar and a vector so that this works.
Oh.
Okay, so we're going that way with it, right? So what we know, right, is m to the negative 1 and k. We know that. So I know what that's a matrix. That whole thing, you get m to the negative 1 times k is the same as a. And I want to find a phi and an omega squared that this is true with, right? And to make that true, because the way we set it up above, that has to be true, right? Or another, A is a matrix, and then x and lambda are properties of that matrix that we can make this thing true. That work better? Okay. I will not ridicule you for that question. That's a good question.
Thanks.
Yep.
Does this only work with column vectors?
Yeah. So yeah, exactly. In order to get this matrix math to work, those are column vectors, so that you can do it right. The inner matrix dimensions must agree. So it says MATLAB. What are you doing with your pencil?
Oh.
What's that doing? You got a little holder?
Yeah,
Oh, look at
Do
that.
that all year.
I did this one time at work, and I was like working on some other stuff, and I headbutted.
Seems
my pencil.
dangerous. Seems
Right
dangerous.
in
That's
the
right.
face. Yeah.
Good thing it didn't get you in the eyeball. Okay. So then let's define a couple things. Right? So if I do that, yep, so then this is just to kind of clear that up. That's a matrix, right? So this is a column vector. Right? And then lambda is a scalar. All right, let's define some of these things. This is heavy. That's why we take so much time to go through it. So, eigenvalues. Eigenvalue is lambda. I'll fill that in a second. Eigenvalue in this case is going to be lambda. Okay. And then the eigenvector in this case is going to be, not m. Is going to be, in this case, the x. Ooh. Okay. In our case, right, this is going to be omega squared. And this is going to be phi. That phi that we had set up. Just kind of explain those things. And then, just kind of some notes on these. These are properties of matrix A, or m to the negative 1 k. M, yeah, we'll just call it m to the It's written better down below. Right, they're properties of those matrices. Okay. We're gonna let computer calc for us. Right? In particular, MATLAB is gonna do it. We're gonna use MATLAB for it. Other things, n by n matrix has n eigenvalue, eigenvector pairs. Right, which brings up another good point. They come in pairs. Right? What do I mean by that? We will have lambda 1, which will be associated with phi 1. We'll have a lambda 2, which is associated with, oh, sorry, I'm mixing things, x1. You're going to have a lambda 2 corresponding to an x2, right? Or in our case, you have omega 1 squared associated with a phi 1 and omega 2 squared associated with a phi 2.
So is omega still, like, dealing with frequency?
Yeah, it is. Yeah, well, we're going to get to that because we haven't really talked about what it represents at this point, but that's exactly what it represents. It is the frequency that mode vibrates at. Yep, that's exactly right. Phi is the shape that it's at, and then omega is the frequency that it vibrates at. All right, so that's the general stuff there. The other thing, I guess, maybe to note here, so because it's kind of tied into this one, let's add a little note here. An n by n matrix, n in our case, is the NDOF, the number of degrees of freedom, right? Yeah. Right, because sorry, but like if we have a 3 degree of freedom system, we have a 3 by 3 matrix, and so therefore we have 3 eigenvalues and 3 eigenvectors. Sorry, Amanda, what was that?
Are you like dropping that notation? That bar?
A bar? Yeah, no, I should have it. I should have a bar there and a bar there. What's that? I wasn't done yet. That's right. Thank you, Jacques. Thank you, Jacques. What's missing?
X2, that's the.
Yeah, what's missing from this? There we go. That's right. Thank you, Jacques, for the support. That's exactly right.
We seem to make an algebra mistake, like,
Did you make an algebra mistake?
Yeah, he said that was a real damage.
I said that's a real
Oh.
fake move. Tim was like, very upset about it.
Oh, that you told him it was. Oh, interesting. I mean, I never make algebra mistakes, so.
Oh, right.
Yeah.
You made 2, that's not what you're
What's that? What's going on?
That's
That's
not
no sound like that.
Oh, yeah. Congrats. Okay.
Pardon myself.
Okay.
Put all that numbers markers.
All right. So we're in the middle of this stuff. We're kind of getting a feel for it, right? So yeah, let's come back to our case, right? Our case is the same thing, right? Again, the matrix for ours, just to kind of reiterate, is going to be m to the negative 1 times k, right? If you carried that out, that is that math is a matrix, right? And then that gives us phi, right? Phis, I guess, lots of phis, depending on how many degrees of freedom we have. These are the eigenvectors, right? Which are going to be the mode shapes, right? Our omegas squareds, are the vectors. Right? These are our eigenvectors, which is going to be the, I wasn't done yet. Eigenvalues, right, And these are going to be our circular natural frequencies. Natural frequencies. Circular natural frequency. Yep. And the number of degrees of freedom gives you that many modes and mode shapes. And we kind of talked about that already. Okay. So then once you get, once we solve for that, this kind of is jumping ahead a little bit, but like I'm missing a summation right here. All right, since I assumed the shape of it up above, right, and we go through and make that stuff work, I then have to bring it back into the real one, where this is going to be more clear in a little bit. But if I want to bring it back, I have to bring back what's happening in mode 1, mode 2, mode 3, mode 4. I have to add them all up afterwards. What that looks like is our assumed displacement, right? This was our assumed displacement, which is just phi times e to the I omega t, right? Again, this will be more clear when we use the Euler identities to get it in sines and cosines and stuff like that. But what that looks like is we just then add up all of the different modes and the overall solution. We're just using our assumed form of the solution and then coming back to this, and then we add it up afterwards. We're going to come back to this later. Let's talk about what all this stuff means here. All right, so then here's a little example. Okay, so you have an example. So we have, this is just a 2 degree of freedom system. This comes right out of the book. 2 degree of freedom system. We have the whole first floor is 2K, and then the second floor is just K, and that's for the whole floor. That's both of those things added together. It's just the way that this model is set up. And then we have 2 mass on the first floor, and then 1 mass at the top, and the mass is 10, and then 2 masses obviously equal to 20. And so you would set up, this is just a 2 degree of freedom system. This assumes, in order to make this a 2 degree of freedom system, we assume that these things are infinitely rigid and these are inextensible, and then you get the shear displacement like this. So we simplify it down to just a 2 degree of freedom system, right? You assemble the stiffness matrix, right? It's just set up like that. If you plug in the values for K, you end up with this, right? 3,000, 1,000, positive down the diagonals. They're coupled through the second floor stiffness, which is that K, which is just 1,000, so that's a negative 1,000 there. Our mass matrix, you'd set up like this. What gets a little, this throws me off a lot, and I'm sure I'm going to make this mistake a lot, is that this is floor 1 and floor 2. This is floor 1 and floor 2, so they get reversed, right? So like a common mistake that I see people do is they flip it like in physical space. This one's on the bottom and that one's on the top, but in our matrix, that's on the top and that one's on the bottom. I mean, see how it's upside down in terms of that. It's like the bigger mass is on the top of our mass matrix, like this 20 right here. You think that it's like, I would never make that mistake, but trust me, you're going to make that mistake. Because later on, when we get displacements, we're going to get U1 through whatever, and the bottom one is going to be the top displacement, and the top one's going to be the bottom. Got it? Let me draw your graph.
Free vibration.
Yeah. Free vibration, right? So anyways, so there's our mass matrix, there's our stiffness matrix, okay? At this point right here, you would make this thing up, and then you would go to MATLAB, or even your calculator. Your calculator will do these things, your TI-89s. Your solar powered will not do this, but your TI-89s. I doubt a TI-84 would do eigenvalues and eigenvectors. But don't do it that way anyway, because we're going to use a computer to do this, right? The command, there's a couple commands. I'll show them to you. There is eig, and then you could just do m to the negative 1 times k, and those would be set up as matrices like you have up before, right? And then there's also this way. I'll show you both of them in a second. Eig k comma m. They give you 2 different answers, which you're like, why would they do that? I don't know. We'll look at the 2 different ways. But what both of those do is they return to you the eigenvalues and eigenvectors for the system. And they're slightly different. They normalize them differently. What's that?
There's a comma.
Yeah, it's k comma m. This one, that's a comma in between them. Let me show you what they do. This is kind of. All right, so I set up the same problem in MATLAB, right? I set up my K1 and K2, my M1 and M2. I set up my K matrix like that. So there's the same K matrix, and there's my same mass matrix. And then there's my I, and then literally in MATLAB, it understands it knows that that's a matrix, and an m to the negative 1 will be the inverse of that matrix times that K value, right? And then it returns to you these things. The thing to be careful of is you have to try to catch. MATLAB's weird sometimes where if I didn't put anything out front here, all it returns to you is your eigenvalues. But so you have to tell it, I want to catch two things. If you say I want to catch two things, phi and omega squareds, then it will return to you two things. If you only say you want to get one thing, it'll just return to you the scalar. So you just gotta be a little careful of that. So there it is, right? I, K, comma, M. And so it returns to me my phi factors, or my phi, not my phi factors, it returns, let's not confuse those phis, right? Those phi factors are in strength design, like not those ones. These are our mode shapes, okay? And these are our mode shapes here, and here's our omega squares. I will say, and they go in pairs. That 50 goes with this, and that 200 goes with this. Now, doing it this way, I m to the negative 1k, it actually does it with it gives you the fastest one first, and then it gives you the slower one second, which usually we talked about before, it's the other way around. So I would not use just the I m to the negative 1k. Really, that's what we're doing, but just the way MATLAB does it does it different. It just returns to you kind of like opposite the way we think of it. If you do I, K, comma, M, it gives us the slowest one first, and then it gives you what we're calling mode 1 and then mode 2. So I would use I, K, comma, M. But notice that they look different. They look different, right? So this is mode shape 1, and it's 0.291 and 0.2582. And this one returned 0.44 and 0.89. And then this one did one negative and one positive of the same value. That gave one negative and one positive of the same value. So one thing we're going to learn, actually, the next thing we're going to talk about is there is no unique solution for eigenvalues and eigenvectors, which you may remember back to, Amanda doesn't even remember doing eigenvalues and eigenvectors. Right, but that is something that you learned when you did eigenvalues. They're not unique. They're scalars of each other. So this guy right here is half and then double, right? In the same direction, half and then double, right? This is just double that one. And that's what's happening with this one too. That's just half, and then this is double that one. And so they return to you these things normalized in different ways. And they return to you a different order as well. I like this one better. I, K, comma, M. Right? And we'll talk about how it's normalized, right? You can normalize these things all sorts of ways. I could make the top floor equal to 1. I can make the top floor equal to 1, which is the bottom here. Remember, Jay? That's the top floor equal to 1. And then this one would be 1/2, because it's half of that one. So I could do 1 and 1/2. And this one I could make 1, because that's the top floor, and that would be -1. And both of them work. But your scalars would stay the same. The scalars, you notice, are the same, right? But they're just reversed. This one gives them backwards, and this one gives them the way that we want them, right? That's one way we normalize them, is to make the top floor 1. The other way is, we'll get to that in a second. That's what this one does. It does this fancy way. We'll talk. You'll see it in a second. I'll say that's what it's doing. Okay. Any questions about that? So you just let the computer do that, right? So the book, when they did their example, they did it so that the top floor was equal to 1. Right? Here's the phi 1. They made the top floor equal to 1 and the second floor equal to 0.5. Right? So they normalized this thing so that the top floor was equal to 1. So that's 1 and 0.5. So kind of indirectly, that comes from that kind of indirectly. They just normalized it differently than I, K, comma, M does that. But then omega squared. I mean, we could say, actually, let's write this down. All right, so really, these things would give something that looks like this. Here we go. It returns phi 1, kind of stacked that way, and then phi 2 stacked this way. Right, in our case, that would be equal to 1, 0.5, negative 1, 1.
So are those p-values like some factor of displacement of that floor?
Yeah, it's a good question. We'll talk about what they are in a second. Yeah, we'll talk about what they are in a second. Okay, but that's it stacks them that way, right? And in our case, it's 0.5. Oh, did I do that? Yeah, 1. Sorry, I flipped that. It should be negative 1 on the top, and then. One. So this case, they were normalized that the top floor was equal to 1. So that's what that vector would be. And then it would also return. That would also return a matrix of these guys, which is omega 1 squared and omega 2 squared. Right? And so in this example, that would be 50, 0, 0, 200.
So actually, your period, you have to square root.
Yep. Yep. And so, assume that our calculator or whatever kind of gave us those results, right? I'm not talking about, we're not going to figure out how to calculate eigenvalues and eigenvectors. It's actually not bad. It's not bad. You might remember it's like you minus a lambda from the diagonals, and then you do the determinant. You set the determinant equal to 0. Yeah, see, you remember that, right? Yeah, you set the determinant equal to 0, and then you solve for your lambdas, and then, anyways, there's ways to do it. MATLAB does it for us. And so what does that mean? Okay, so then phi1 is 0.5 and 1, and it has omega 1 of 50. And so you come over here and say, yep, phi1 is 0.5 and 1. It also says omega squared is equal to 50. So then I just do the square root of that, and then 2 pi over the square root of that gives me T1. That's what this is doing. 2 pi over the square root of omega 1 of 50 squared. Oh, 50 over 50. Yes. Yep. That's how you get that period of T1. Okay? And then you do the same thing over on the other one. Right? That's what this is. So then mode 2 looks like this. And so back to your question there, Ben, well, what the heck does this even mean? What is 0.5 and 1? That is what the mode shape looks like. Okay? And so for this is mode shape 1. It says that it's going to be 0.5 on the first floor and then 1 on the second floor. So that mode shape would look like this. Mode shape, this right here would be 0.5, and this point right here would be 1.0. And so then that mode shape is this. Okay? That's what mode shape 1 looks like. You just displace the first floor with 0.5, and you displace the second floor 1. Okay? Then we come over and say, what does mode 2 look like? Well, mode 2 was negative 1, 1. So mode 2, this is negative 1. And the top is 1. And so that mode shape looks like this. Oop. So that's that general shape. Okay? And then where does the omega come in and what the period does? Well, what it is, we haven't talked about what Q is. There's a Q going to be floating around, but that's kind of what the time-changing part. We have the shape, and then we have the time-changing part. And this is the time-changing part. It's just, we're going to get to it a little bit later, but it's the solution to a single degree of freedom system, which is just is a cosine wave like this, right? So this is what the time-changing part is. This is, in the equation up above, that's what this stuff is doing. This I to the omega t, when you apply the Euler identities, it's just an oscillation. And so here's the oscillation. It's going like this, right? This is the overall thing. So what we look at is mode shape 1. This is mode shape 1's time-changing part. And so what they're trying to show is like different locations. So right at the very beginning, it's just 1 times that, which is that. Okay? And so it just looks like this. So that right at time step 1, right there, or at 0, at time of 0, it looks like this. Then a short time later, right? At point B right here, it's multiplied by less than 1, right? So then it moved to this shape that looks like here because it's multiplied by less than 1. Then we go point C right here, it is equal to 0. So it's 0 times this mode shape, which is going to look like this. It's just straight up and down, right? 0 times 0.5 and 0 times 1 gives me, gives me 0 as a C. Then we come over here to point D. Point D is over here, so it's negative 0.5 or something like that. So then this is negative 0.5 times this original shape. And then this one over here is going to be negative 1 times that original shape, which is going to be negative 1, negative 0.5. And so this thing, and then after that, it then starts coming back the other direction. So you can imagine this is what this mode shape looks like, is it comes back, it rocks this way, and it rocks that way, and it rocks this way, and it rocks that way. And then it rocks this way, and then it goes back that way. So that's what that mode shape looks like, right? You have the shape of it, which is defined by the vector, and then where the omega comes in is the frequency that it does it, right? And that's what this is right here, 2 pi over omega 1. So in our case, on the example up above, this distance right here, between here and here, that is 0.89. Right? And so that's a slow rocking back and forth. And it's just modifying that original shape of 0.5 and 1. Right? And then if you were to, this has built into it, like the shape of it, using the fixed rotations and stuff like that. But, it's really just that nodes that are moving back and forth, and you have a shape function between it. Just real quick before you go, what does mode 2 look like? Well, mode 2, right, is 0.1, is 1 and negative 1. And then you do the same thing where you multiply it. You multiply it as you go across. And so, it's changing with time, and so it's doing this, right? It's going positive and negative, the point out front, the time changing part starting out positive, going negative, and so it's just multiplying by those values, and so it's doing a wiggle like that. As you see, it wiggles back and forth. How it's wiggling back and forth is based off of this frequency. Right there. And in our example up above there, that is 0.44 seconds. So that's what the period of that.
Is the displacement of the top one like relative to the floor below it, or is that
Overall.
overall?
Yeah, overall based on the top. So it's if you just had a plot of x's, that would be 1, and then that would be negative 1. Yep. And so it just goes back and forth. Yep. So it just wiggles back and forth. Right, and we'll look at that. I'll show you the 3-degree freedom system. That it's actually going to be your homework is to do that. Is you do the same thing, the same process that happens. But we'll show you that just so you can see all of them kind of going together. But this one vibrates back and forth fast, right? And that's why we kind of put them in order. We start out with the slowest and then work our way up to the fastest. The way we do it. And then we pick up a node here. There's a point in there that doesn't move. That's the node, and then you pick up more nodes the more it oscillates. Okay.
Oh, shit. Yeah, can you go back to that?
The what?
The matrix on the right, I never got.
That one?
Yeah.
Yep. So when I taught Tom this class, Kujala, we were kind of like midway through the whole thing, and he goes, "What the hell are we doing?" He literally said that to me. It's the first year I ever taught, and then he goes, what the hell are we doing? I think I've improved since then. I will say, when Tom went through it, it was very rough.
Was that 10 years ago?
15 years ago.
Jeez.
Yeah. Yeah, 15 years ago I taught this to Tom, and he literally was very rough with me. He was very rough with me.
Both of those matrices are from the K times.
Yep. A, K, comma, N. It returns to us a phi stacked like this and an omega stacked like that.
Is that 3 columns? How do you get 3 columns?
2 columns.
Or 3 rows, I mean.
Yeah, this is exactly. Yeah. There's 2 rows. That one and that one. 2 rows. 2 rows is 2 by 2. This is a 2 by 2.
Wow.
Huh?
Doesn't look like it. It looks like a 3 by 2.
Oh, I just mean up and bottom, right? In our case, it's 0. If it was a 3 by 3, yeah. I'm just saying that they're stacked. You stack them vertically there, and so this one is that, and this one is this.
You can be around for like the next hour-ish.
Yeah.
Okay.
Yep.
double check that I modeled it right. So I have the whole bottom set sixed. Hold up. Is it safe to treat the bottom of the shear wall
Yep,
sixed?
yep,
Okay.
yep, and it'll just do pins at the bottom. Pins at
I
the
mean
bottom.
pins.
Yeah, yep.
And then on if this is the brace frame side,
Yep,
are we basically treating end releases on each one of these?
yep,
Okay.
yep.
Then this
So
is,
the only
this
moment
part is
connections.
the moment over here. Right?
Yep, the only moment connections you have will be on this side over here.
Yep. And it's just that one. It's all three
All
bays.
three
but
bays,
it's
that
just on
one side.
opposite.
Yep,
Okay.
that's it. And then everything else in there has like moment releases, just simple connections on everything, with the exception of all the columns. The columns going up, you
All
model
the
them.
internal beams are going to be.
Yep, they're all
fixed?
released.
Oh,
They're all released. Yep. And then all the columns you model as one single member, so they'll have the moments will be carried across all the columns. Yep. But then all the beams feeding in and all the other things will have releases on them. Yep. Yes.
Include diagrams.
Is to get the stiffness of the
The
left
whole-
column or
the whole floor.
both of them?
Yep, the whole floor.
summation of the stiffness of both of them, yeah?
Yeah, both of them. Yep, it's the same. Otherwise, it would be 2K and 2K on both sides added together. So it'd be 4K total. But we're just modeling that whole floor stiffness is 2K, and this whole floor stiffness is K.
How do you calculate the displacement of the column in the middle, for example?
Oh, in the
Not-
middle. Yeah, I mean,
Is it a specific equation or?
it is a specific. It's the shape function. It's a shape function that you get from you if you fix rotation. And you fix rotation. There's a shape function in between the two that kind of says it starts out with 0 rotation and then it comes around and then it goes up.
Quadratic?
It is a quadratic. Yep.
Yeah.
Yep. And so it'll have zero rotation and then 0 rotation. So it'll plot like that. You don't have to do it. I just doing it for my graphs. Just
Yeah, I
it-
saw that. You,
yeah. It's, you know, it's interesting. Like to solve that problem, it's like the code itself is pretty small. The plotting is pretty big because you have to model that call. All I really have as a result is displacement of that floor, and that floor. And then I've got shape functions for each one of those things. And then there's both columns and then the beams in between. So all of the rest is just plotting. So
and I didn't get that where this minus came from. Because we didn't have you didn't put.
yeah, but
any
it's
minus there.
is it from the imaginary? If you square the imaginary, then that you pick up the negative from that. Yeah. Yep.
Okay.
Yep, that's where it's coming from. Yep.
Okay, I got a couple questions. So on that, was that 3 rows of two?
Yeah,
two
no,
columns?
you're right.
I heard
threw,
them talking
yeah, I
about
threw it
that.
off. I just meant like that Phi 1 is stacked here and Phi 2 is stacked there. Phi 1 just
Okay.
happens to be a 2x2 and a 2x2. So that Phi 1 is just this, and then Phi 2 is just this. And I just wrote them that way just to say they're stacked. I stack
Okay.
Phi 1 and I stack Phi 2. And this isn't
that's
one.
not a one,
That's not
that's
one
not a
Phi 1. That's just saying that I stack Phi 1 like that and I stack Phi 2 like that.
Okay.
Yep. And then which makes more sense. In here, it's a 3x3, and so it'll be yeah, Phi 1 stacked, Phi 2 stacked, Phi 3 stacked.
Okay.
Yeah, I think I have it. Yeah, I do the same.
Okay.
I say the same notation. Those aren't
Okay.
ones. I just mean
I
that
didn't
there's.
look forward in the notes.
No.
Okay.
Yep, that's all I meant. And then later on, we do this thing where we transpose this matrix, and so that ends up being that our fees are sideways, and then I just draw them this way. They're sideways,
Okay.
right? And so what that'll look like. I don't know if I ever do that. I don't ever write it out. But that's the point. It's just that they're either stacked or they're vertical.
Okay.
Is all I wanted to say there.
All right. And then
Yep.
on the project, the moment frame connections are all rigid,
Yep,
and then everything else is released.
is released.
What about the beams coming into the moment frame?
Those will be fixed. That are
Those
coming
will
into.
be fixed also?
Yep. So you'll when.
So that whole connection there on
Yep.
the moment frame will
Well,
be
don't you draw the
fixed.
columns continuous so you don't?
Yep, the columns will always be continuous everywhere in the whole structure. So like, you'll have all those going up, and on the moment frame side, you'll by default these things are connected. I think,
Yeah.
right? And so you'll
Okay.
have, and then they'll have 3 of them and stuff. They're coming in, so there won't be any releases on this thing.
I think it defaults to fixed.
I think it defaults to
But
fixed.
okay, so the connection, going into the page
Oh yeah, going to the page will be released.
will be released,
Yep.
because there's a connection on that column.
Yep.
It goes into the page.
Yep.
But that'll be released.
Yeah, that's right. Because there'll be a beam coming in, and it'll just be a simple support, right?
Okay.
Because to make a moment connection is quite difficult, right?
Yeah.
I mean, you have to weld the flanges to the flange of the column, and you have it's not just as simple as just putting some bolts in there.
Right.
It's pretty intense, the thing, and so only certain ones will actually behave that way.
Okay.
And then they're more expensive, and so you only put them in where you need them, and everywhere else you model them as being released.
Okay.
Because they'll act as a simple support.
And you do
Yep.
simple so that you don't get the over rotation.
Yep. Yeah,
Okay.
that's right. That's right. Yep.
Okay, that makes sense.
Yep. And then and again, your columns, the way they put those in, even if
Those will
they're going to
be-
come in.
So they're not modeled as separate columns. You
Correct.
Just run them
You run them up the whole length. Yep. And then
Okay.
they'll probably end up being separate the way that the models work. But as long as you don't release the moments on the end, it'll behave as if they're constant all the way up.
Okay, so I can just draw a straight line in VA.
Yep. But I think
And
when you
then
put
the
this
way
beam,
these come in,
when it comes in,
beams
I think
come
it'll
in,
break it.
It'll make a connection.
Yeah, it'll make a connection, right?
Okay.
I think at VA will do that, right? If you touch
I
it,
don't think it breaks it, but it'll attach it.
it'll attach it. Yeah.
Something weird like that.
I thought they have to be touching at a node in order to do it. So I think they put a node there.
And then you just have to make
I
sure
I
that
put
that's.
nodes there, and then I
Yeah.
connected my columns and stuff, and then I think when
Yeah.
the column runs over the node, it
Yeah.
connects it.
And then you just have to make sure that those aren't released.
Yeah,
Those
on the
are
moment
rigid.
frame side. Oh yeah. You're right. Everywhere,
everywhere on the
Yep,
columns.
yep. By default, they should be not released. But,
Okay.
And then I don't know if you saw, this shows up as like a little green.
When you release.
When it's
click on
released,
it.
there's like a little green thing that shows up to
Yeah,
show
Yeah,
that.
yeah.
Yeah, when you select it. Yeah.
Yeah.
And then that means you've done it right. So basically, everywhere should have that except for your columns and the moment frame side. Even your
Okay.
braces that go across, you want those things released.
Yeah.
On the
Yeah.
brace frame side. Yep.
And you don't have those
Perfect.
touching, right? Those are separate.
Yep, that's right. I think I had set it up that aren't separate or aren't touching, but they'll behave the same structurally, like in terms of stiffness.
Yeah,
if
because
they're-
I think it makes a node when you create those.
You're in the
it
middle.
makes a node in the
Could be,
middle.
yeah.
And then we also, for the shear walls, we don't have columns, correct?
Shear walls don't need columns. Nope.
Okay, but I did do the tiny beam thing you mentioned.
Yeah, so you can do a line load across there.
And
Yep.
then for the shear wall, also fix every node at the base after meshing.
I think, pin them. Yep.
Fix.
Oh, you fix them?